Yes. So we saw certain terms, that is energy and work. Then what is thermodynamics? Okay. And I said that thermodynamics is the science of energy. Okay. And it deals with converting one form of energy into another, maximizing the desired output, relation between the properties of a substance, and flow of heat and work, right? Then we talked about the implication of first law, and I said that what actually first law is. So first law is the law of conservation of energy, and I said that if you make a universe of processes, then what will you find that out of all the processes, first law says these processes are valid and these are not valid, or these are feasible and these are not feasible. So it's basically breaking the whole set into two parts. One is the feasible processes, the second is infeasible processes. So infeasible processes are like our imagination, dream processes, whatever we can think of, that is there in the uh, so you can think of any process, it may fall into one category that it is feasible, or in the other category it is infeasible. Now the when second law comes, it says, okay, I have also a role to play, and it says no, you divide this now into four parts. So you have four sections where first law is valid, second law is valid. That is the section which is the real world, where all the processes existing in that quadrant, where first and second law both are valid, those are feasible processes. And if in all the other quadrants either one is not valid or the second is not valid, then those processes are infeasible. So second law is also telling us that even if the energy is conserved, the direction is fixed, right? You cannot go back, just like you cannot travel back in time, right? Similarly, there are processes that which, in other words, if you have heard that entropy cannot decrease, and sometimes people like to equate time with entropy, that time will always go forward, the entropy will always increase. So this is certain constraint which the nature has put on us. Okay, so uh, then we talked about that there is another thing which the second law is telling us, that energy has both quality and quantity. So far we used to know that energy has so many joules is the energy, but that's not the case. There is something more to it. And something like that, if you have a quantity of water from two different sources, I told you, they vary in purity. Why you take it from the drain or you take it from the tap or a filter, each water has its own quality, even when the quantity is same, and they are not priced similarly. Similarly, if there are workers in a factory, you will find that each one is not paid equally. Even while each of them is working for 8 hours a day, they get different pay. Their qualities are different. And similarly, all of you are sitting in this class, you'll be attending all the class, but all will score differently. Right? So there is a difference in quality also. Now, then coming back to these were the natural examples. Let us come back to scientific examples. That we know that work can be converted to thermal energy completely. This is the experience. People have observed it, that whatever work they have, they can easily convert into energy, thermal energy, right? But when you look at it otherwise, in the reverse way, the thermal energy cannot be converted to work completely. So if you want to convert thermal energy into work, it is not possible. Complete conversion, right? What does that mean? That work is better than thermal energy. So you come to the conclusion that work and energy are not same. So 1 unit, 1 joule of work and 1 joule of thermal energy, they are not same. They are different as far as thermodynamics is concerned. If you are going to weigh them, yes, they will be same. But still, when you are going to use them, you will find that no, this one is better than that. Okay. Same thing is true about thermal energy, which is having different temperature T1 and T. So energy at temperature T1 and T2 are different. Why they are different? Because you can convert energy at higher temperature to a energy at a lower temperature, but the reverse is not possible. Your heat can flow from high temperature to low temperature, but the reverse is not true, which means that there is something different between the two, right? So, and we know that energy at T1 has a better quality because it from T1 you can get energy at T2, but from T2 you cannot get energy at T1. So your energy at T1 has a wider scope, or wider, you can say, applicability. Okay. So this is another, you can say, the difference or the conclusion or the understanding we get from the second law. One is that even when, please mark the word, even when the energy is conserved, all processes are not feasible. Okay, I gave you the example, and one of the examples you can take, that you cannot draw energy from an atmosphere or a sea and convert it to work completely. We are not talking about increasing the amount of energy. We are saying conversion of one energy to another. Drawing thermal energy from atmosphere, converting it into work. Right? It is not possible. So that is what second law is saying, that even if you are not violating the first law, there are certain more restrictions. And then it says the same extension to that is that energy has its own quality. These two things which second law tells us about our day-to-day understanding of, you can say, world or thermodynamics or what. Now then we talk about what is the application of thermodynamics. Now one thing is there, that all processes occurring in the universe, thermodynamics is not limited to mechanical engineering or what we study here. Anything you pick up in the universe, any system you pick up in the universe, thermodynamics applies to it. Okay, so this is the wide scope of thermodynamics. It's a fundamental thing. Just like Newton law will apply everywhere, Coulomb's law will apply everywhere, right? Conservation of momentum law will apply here everywhere. Conservation of mass will apply everywhere. Similarly, the laws of thermodynamics apply to all systems, no exception. Yes. Then let us take the example. Then if you talk about system where one form of energy is converted to another, you will find examples like gas stove, pressure cooker, water heater, oven, fan, radio, television, air conditioner, cooler, automobiles, aircraft, rockets, space vehicles, ships, human body, etc., etc. So I just given you a sample of that, but you can say that all systems are come under the purview of thermodynamics. But what happens is that you will find that electronics and computers people do not study thermodynamics. Although the thermodynamics apply there, but they don't study it. And the reason being that uh, when you talk about radio, television, transistor, computer, etc., here the efficiency of energy conversion is not of prime concern. When you buy a computer, you do not look for what is the watt of the computer, what is the consumption of the computer. What you look for: CPU speed, RAM size, hard disk speed, and all that, monitor quality at that. That does not mean that it does not consume energy, but that becomes a secondary thing, right? Similarly, for TV or mobile phone, of course, in mobile phone, we are bothered about the power consumption because many a times it remains out of circuit, out of the electric circuit. So depends whatever the use is. So the thing is, these people in these branches, they are not talking about thermodynamics, but that does not mean that thermodynamics does not apply. It applies. Okay. But when you talk about power plant and automobiles and air conditioners, these are the system traditionally mechanical engineering are studying. They are power guzzlers. They consume a lot of power, and their efficiency of conversions come into play. That is important. In automobile, when you go to the market, you always talk about what is its mileage, how many kilometers per liter of petrol. What is that? That is how much efficient it is. When you talk about power plant, you talk about the efficiency of conversion, because you are assuming consuming lot of power and converting it into, the power is the main, you can say, consumable part in that. When you buy a motorcycle, after you have bought it, or a car, what is the cost? Cost is that of petrol. Rest all is very minimal. So you are bothered about reducing that cost. And what does that mean? That I consume less petrol and travel more. So it is talking about the efficiency. And this becomes, you can say, a prime subject of thermodynamics. That what is the efficiency of the system. Okay. So we study it a lot. And that is why you find that for mechanical engineering, this is a prime subject. Okay. Then we talk about vocabulary of thermodynamics. There are certain terms we should know, and you can note them down. And the reason being that we should know that what I mean to say when I use a word. Okay. Because communication may, it is very important that what is being said, that is being understood. तो कुछ words हैं जो कि thermodynamics में बार बार आएंगे. We should be able to understand them, what they mean. The first word comes is the system. We will talk about system many a times. And what is a system? It is a region in space containing matter. So you have some material. If there is no material, you cannot apply thermodynamics to it. And if there is a material, there will be space it will consume or it will occupy. So a region in space containing matter chosen for the study, which we are going to study. Right? So for us, it is a system because we are studying it. Then there are three types of system. One is a closed system, which is also called control mass. We have open system, which is called control volume, and we have isolated system. You have heard about it, but let me just repeat them to refresh. In control mass, or a closed system, the boundaries are impervious to mass. Energy can flow in and out, but mass cannot flow in and out. So what is happening when you have a closed system? The mass is conserved, and moreover, the identity of mass is also conserved. It's not that in this class I send 5 students out and fill it with another 5 students. That is not conservation of mass. That is not a closed system. The same 70 or 80 students who are here, they will remain here. Then it is a closed system. That means all the molecules remain same, identical. You can't change the molecule. You can't replace one molecule by another molecule. No. So in a closed system, mass elements remain same. Okay. So not only the quantity of matter, but the identity of matter remains same within a closed system. So only flow is that is of energy. When you have open system, both energy and mass can flow in and out of the system. Something can go in, something can come out. So neither the mass is constant, nor its identity remains same. Right? And in the isolated is a special case of closed system in which no energy flows into the system. So neither the mass is flowing nor the energy is flowing in. Absolutely isolated from the surroundings. Okay. Then please note that thermodynamic equations which are applicable to closed system are not applicable to open system. You have to develop them separately. Right? The equations for closed system and open system are different. But for isolated system, same as closed system. You can use. Okay. Then we talk about surroundings, because there is always a if you have a system, there is something around it also. So what is the surrounding? Mass and region outside the system. Whatever is outside, but it should be interacting with the system. It should be affecting the system. You only then call it as surrounding. Okay? तो ये नहीं कि पूरा जो यूनिवर्स है जो इसके चारों ओर है वो सराउंडिंग, नहीं नहीं वो नहीं लेते हम, बिकॉज दैट इज नॉट फिजिबल. ऑफ कोर्स इट अफेक्ट्स. इफ यू गो डीपर टू फाइनर डिटेल्स, you don't know, the whole thing is connected. Quantum physics says that everything is connected. But then we have to talk about practical thing, what we have studied, and even if we consider the whole world is connected as a surrounding, it is not going to improve our outcome or the solution. It's not going to help us. The problem which we have before us, that is a conversion of energy, improving the efficiency, etc., etc., that thing is not affected. So we talk about only the surrounding which is interacting with our system. Okay. Then we talk about boundary. Now boundary is what? It's an imaginary or real. It can be both real or imaginary, and it is separating system with the surrounding. So you should be able to differentiate between the two, that this is the system, this is the surrounding. So this is and there is a boundary in between the two. Okay. Now your boundary can have a thickness, it may not have a thickness, but what is essential is that it does not participate in the exchange of energy. Because if a boundary is participating, then what you will have to do, you have three options. Either you take it as a part of the system and introduce another boundary, or take it as a part of surrounding and introduce another imaginary boundary, or you take it as a separate system. So you have system 1, system 2, and surrounding. Let me put it on the diagram. What I am saying is, suppose you have this is the system, right? And this is the boundary. This is not a, you can say, a boundary which is thin, massless, and spaceless. No, it's a physical boundary. It's a wall or some metal body is there. Okay. And this thing is surrounding. So what you do is either you take it this surrounding. So your surrounding is revised. Now this boundary is part of the surrounding and your boundary comes here, imaginary boundary. In the second case, you can say that system is revised and the system becomes now system is revised and you have a new system and here you are mixing this boundary with it. Whatever the existing boundary is that you have made part of the system. Then what will happen? A new boundary will come. Right? Or what you can do, this is another system. So you have one system here, system 1, you have one system here, system 2, and you have surrounding here. So unless until it is not participating in energy exchange, it has to be taken either of the three cases. Either you make it a separate system, you include it as the original first system, or you include it as a surrounding. ठीक है, तो ये हमें ध्यान रखना पड़ेगा. Okay. Now let us say how our closed system looks like. We are seeing it diagrammatically. मैंने आपको explain कर दिया है, but diagram is better. Here you have a surrounding, right? And it is exchanging heat as well as work with the surrounding. So the system is above, it is enclosed in a somewhat spherical shape, and it is exchanging energy in the form of heat and work with the surrounding. But there is no mass in or no out. This is not possible. So neither the mass is going out nor the mass is coming in. So I have written that my m in or m out both are 0. Then it is a closed system. Now we go to the next system. This is your surrounding. You are exchanging heat with the system. You are exchanging work with the system. Mass is coming in, mass is going out. This is an open system. We can study this also, the previous one also. And what will be the isolated system? Isolated system is this. This exchange of Q is 0. Exchange of W with the surrounding is 0. And there is no mass in and no mass out. Then it is isolated. Okay. Now we talk about property. What is the property? Because we'll be using this word quite often. So we have talked about system, surrounding, boundaries, and system. 3 types of system: closed, open, and isolated. Okay, or control mass, control volume, and isolated. Then we talk about properties. Now property की जो definition I have written here, it is not supported by Sengel and Bowles. They are giving some other definition, or probably that definition he is not giving at all. But still, now what is the property is? Property is any characteristic or parameter. So when you have a system, you are observing that system. So that observation is put under certain category. You can say the mass is equal to this much, volume is equal to this much, temperature is this much, or you can say density is this much, or you can say color is like this, or you can say shape is like this, whatever you are thinking. So some parameter you are studying. Now, the parameter defines the state of the system. So whatever your system is basically qualified by that, right? Of course, whatever properties you give, you can never identify or you can tell about the system completely, right? This is the limitation of language. Whatever properties you tell, 1,000 properties you tell about a system, but that does not explain the system. There is something more to it. And for an example, if suppose I take one of the students, I start describing him, नाम ये है, age ये है, hostel room number ये है, all things, father का नाम ये है, height ये है, all things you describe, but still that person is not fully described. This is what I see him, but there is many things which are within him. वो क्या सोच रहा है, क्या उसका ambition है, they also define him. तो ये हमारी लिमिटेशन है कि हम कभी भी वर्ड्स में किसी भी चीज को डिफाइन नहीं कर सकते. Whenever you are expressing anything in words, you are basically telling only one aspect of it. If I say that a ball is of spherical in shape, I am yet to tell what is the size of the ball. I've only told the shape. If suppose I tell the shape also, then I have to tell what is the material of the shape. If I have told you the material, the shape and the size, then for how long it is lying here? You can keep on adding. What is its temperature? How many molecules it contains? When was it formed? Who created it? You can keep on adding the things, and you will find that you will come and touch a wall where you cannot describe a thing. I am being slightly philosophical here. And why I am saying so, that when you come to the philosophy, spiritual literature, it is said that God cannot be defined. I am telling you, anything cannot be defined. Forget about God. If you want to define anything in words, you will always find they are insufficient. Suppose आपने वो dumb charade देखा होगा ना? You must be playing that game. What happens is there, you have a scene or a situation which you want to describe in terms of words, and it takes a lot of time that you are able to explain. Now, if I ask any one of you to describe a rose in words, can you describe? Simple flower. I want you to. I just want you to tell me what is the color of rose in words. Can anybody tell me? You cannot. If you say it is pink, वो कहेगा ये मेरा वाला pink नहीं है. जो मैं pink सोच रहा हूँ वो कुछ और है जो pink तुम बता रहे हो. I cannot. If I ask you, okay, describe Taj Mahal, in words, you cannot. There is still something left when you go there and see and you realize that what it is. And that is true for everything in this world. That is what I am telling you, want to bring to you a point. थोड़ा सा मेरे दिमाग में आ गई ये बात तो मैंने कहा बता दूं आपको. In this world, nothing can be described in terms of words. Forget about describing the God. And one word it is used for that, unknowable, one that cannot be. So God is always described in terms of negatives. Infinite, immortal, unknowable. Omnipotent, omniscient. So even that is not sufficient sometimes. Even if you say that it is immortal, you forget to tell that it is omnipotent. If you said omnipotent, you forget to tell it is all pervading. So many things are there you cannot describe. Anyway, so coming back to this, still we have to describe our system. Because unless until we describe our system, how will I communicate with you, tell you that this is what has happened to the system? This is what the change has taken place. So एक जितने से काम चल जाता है ना उतना हम कर लेते हैं. ठीक है, we have made some language to communicate so that we are able to communicate something. अगर मैं आपको कहूं मैं आपको बहुत प्यार करता हूं, कैन आई पुट इट इन वर्ड्स? वो पूछेगा कितना, इतना, इतना, इतना. यू कैन नॉट. Okay, so what we are talking about is that there are certain parameters which define the state of the system and they are relevant for the system, for the study. So it actually means that we have chosen ourselves that these are the parameters. हमारा मन किया, हमने ये चूज कर लिया and these are the, हमें देखा कि इससे फर्क पड़ रहा है, इसको ये हमारे लिए रेलिवेंट है, ठीक. बाकी हमने छोड़ दिए क्योंकि वो रेलिवेंट नहीं. ठीक है ना. वी आर वेरी सेल्फिश, पर्पस ओरिएंटेड वी शुड बी. जिसका काम नहीं तो उसको क्या करना है. Now then there is one more important thing. The property is one which is the independent of path. This is the most important property. I can say this is the property of a property. If you are defining any parameter as property, then the first requirement is that it should be independent of the path. Okay, so let us come to the example. Now you take this example that you are coming to this class from different places. Okay. Maybe let us say two students are starting from the same place, they come to the same class. Okay. But they follow a different route. Somebody is coming on a cycle, somebody is walking down, somebody is coming through stairs, somebody is coming through lift, whatever it is, right? किसी को जो है रास्ते में उसका दोस्त मिल गया, उससे वो बात करने लगा, उसने कहा चल आज एक सुट्टा लगा के आते हैं, फिर क्लास चलेंगे, सर तो परमिट कर ही देंगे, 10 मिनट लेट हो गए कोई बात नहीं, तो वो चला गया. So all that you have done is depends on the path. How much time you have taken, how much energy you have spent. Okay. What length of the path, how many steps you have traveled is all changing. But there is something which is not changing. Your starting position XYZ and T1 and the final position XYZ and T2. Now they are not dependent on path. So these things are called property. So your position is a property, but the amount of energy you have spent, the amount of time you have spent is not a property. Okay. Similarly, suppose you want to raise the height of a block. Somebody is doing with the help of pulley, somebody is carrying on his shoulder, somebody is using the incline, whatever it is. ठीक है ना? घर में सामान शिफ्ट करते हैं ना, तो अलमारी शिफ्ट करने में सबसे ज्यादा दिक्कत आती है. तो समटाइम्स यू पुट अ पुली और एक फ्लोर से 5वें फ्लोर पर खींच लेते हैं उसे. कोई होता है सीढ़ियों के थ्रू लेके जाता, डिपेंडिंग अपॉन द थिंग. What is same in this? You have started from the ground floor, reached the 5th floor. What is varying in this? Amount of time, amount of energy spent on that. So the amount of energy spent is path dependent, so it cannot be called a property. But the position is called a property. You want to boil a water, reach up to 100 degrees C. Somebody may use an electric oven, somebody may use a gas stove, somebody may use a chula. The amount of labor, amount of energy spent, amount of time spent, they are all different for all of them. But one thing is same. The final temperature in all cases is same. So that temperature is a property, but the amount of heat given, amount of time spent, they are all depends on path. So whatever depends on path is not a property. Whatever depends, whatever does not depend on path is a property. Okay. Okay. That we have taken this. Then there is something called intensive property and extensive property. Simple to remember. If you divide the system in two parts and the property remains same, it is intensive. If the property changes, it is the extensive property. Okay? So divide the system in two parts. If the value of property which remains the same is intensive and the value of property which changes is extensive. So suppose I have 1 kg of hot water. I put it in 2 glass. The temperature would remain same. It is intensive property. But mass has changed. Iska mass or iska mass अलग. So it is extensive property. Volume has changed. It is extensive property. Density is same. So it is intensive property. So whatever remains same even when you divide the system in two parts is intensive. Whatever changes is extensive. Okay. Okay. And this was about what is a property. We have talked about it, but mathematically and graphically, I can put it. So your system is at this point. Your final state is this. On one case, you are moving via path A. On one case, you are moving via path B. Now, if the change in X via path A and via path B are same, then X is a property. Change in X, whether you go via path A or via path B. So let us talk about height. So whichever way you have gone, the change in value of X or height will be same. So it's a property. But if it is not same, then it is not a property. So ye saying the same thing in slightly more mathematical terms. Okay. Then we talk about what are thermodynamic properties. So we started with the, so हमारी problem क्या है, हमें सिस्टम के बारे में we have to communicate with other people, we have to study the system, so we define certain parameters. Okay, this is important for us, this is important for us. आपका बायोडाटा भरते हैं ना, जब आप अप्लाई करेंगे तो बायोडाटा आएगा, एक नाम आएगा, उसमें फादर का नेम आएगा, लेकिन बायोडाटा में कई वो चीजें वो थी आइडेंटिफाई करने के लिए हो गई, बट वो पूछेंगे आपके ग्रेड कितने थे, ठीक है, आपने कितने साल में यू हैव कंप्लीटेड योर इंजीनियरिंग, ठीक है, व्हाट वाज योर बेस्ट स्कोर इन विच सब्जेक्ट, एंड योर एम्प्लॉयर इज लुकिंग एट दैट. तो दोज आर द, you can say, important parameters, ठीक है, and certain are unimportant. So we have so many of them, and then we classify them between the two. So we have a parameters which are important to us, we have decided that it is relevant to us, no rule कि क्यों ये है और क्यों नहीं है, ठीक है, nobody has asked us to do that. अभी ऐसा लगता है कि जिस किताब में पढ़ो वही बात है, बिकॉज इट हैज नाउ एस्टेब्लिश्ड, ठीक है ना, कि प्रेशर इज ए प्रॉपर्टी. तो देन वी टॉक अबाउट दैट व्हाट इज अ प्रॉपर्टी. सो प्रॉपर्टी इज वन विच विल नॉट चेंज बिकॉज ऑफ पाथ. Whatever path you follow, if the end states are same, the change in property would be same. Then we have talked about intensive property and extensive. Intensive means even if you divide in 2 parts, 3 parts, 4 parts, its property remains same. The value of the property would remain same. Extensive means it is divided in terms of equal to the, if you have a system divided in 2 parts, mass equal हो जाएगा दोनों का, but half हो जाएगा, equal and half. Volume इक्वल एंड हाफ हो जाएगा. तो ये जो है वो हो गई हमारी एक्सटेंसिव प्रॉपर्टी. नाउ वी टॉक अबाउट थर्मोडायनेमिक प्रॉपर्टी. सो व्हेन वी स्टडी थर्मोडायनेमिक्स, व्हाट आर द प्रॉपर्टीज दैट बिकम्स रेलेवेंट फॉर अस? लाइक आई टोल्ड यू, व्हेन वी आर टॉकिंग अबाउट कंप्यूटर्स, यू आर टॉकिंग अबाउट सीपीयू स्पीड, you are talking about RAM size, right? But when you are talking about a geothermal source of energy, you say that what will be the temperature of this source, how much is available, what is the quality of that energy, that will be the question. So those properties of the system that change because of transfer of work or heat between the system and surrounding are called thermodynamics. So the thermodynamics is basically you have a system, you have a surrounding, some heat is flowing, some work is flowing, and because of that, if certain properties are changing, then they are good to be thermodynamic properties. Okay. And what are they? They are 8 of them: P, V, T, U, H, S, F, and G. I hope you know the name of all of them, right? In the upper line, I have written they are extensive property, where they, like enthalpy, there is a total enthalpy and a specific enthalpy. So when we talk about enthalpy, total enthalpy, it is used by H. When we talk about specific enthalpy, it is written by small h. Now small h enthalpy जो है, अगर आप सिस्टम को 2 पार्ट में डिवाइड कर देंगे, it will remain same, but the total enthalpy would change. So that is why the one is in extensive, the other one is in intensive. Okay. Now out of these, PVT, these are called principal thermodynamic properties. And the reason being that these 3 can be measured by some instruments, but all other properties cannot be measured. They have to be calculated. based on equation. If I tell you that find the pressure of the gas here, you can immediately put a barometer and tell me this is the pressure. But if I tell you what is the internal energy, there is no instrument which can measure the what is the internal energy of this air, or what is the entropy of this. You'll have to measure certain thing, make a calculation, and then tell, okay, this is the thing. You cannot measure, you can calculate it. So these three properties, P, V, and T, which are measurable, they are called principal. The remaining five are called simple thermodynamic properties. Okay. I think we should stop here if you have a question, because I will not be able to. Okay, just a minute. After this, we'll be studying what is the thermodynamic equilibrium. It is consist of four equilibrium. If they are happening together, then it is called thermodynamic equilibrium. They are thermal equilibrium, mechanical equilibrium, chemical equilibrium, and phase equilibrium. So what is an thermodynamic equilibrium, and what are these individual equilibriums? We'll study in next class. Okay.